This is an introductory video looking at the concept of concentration. Before we can attempt more complicated calculations like titrations, it's vital that you're confident manipulating the numbers to work out and use concentration. This should be useful for you if you're studying A-level or GCSE Chemistry. Concentration is a measure of the amount of a solute that has been dissolved in a set volume of a solvent. Sometimes it's useful to know this in terms of a mass, and this is often the quickest way to go. So concentration is a bit like speed or density in that it has compound units, so units that are made out of other units, and they could vary depending on what the solute and the solvent have been measured in. So it would be absolutely fair to say that if I had 50 grams of something that had been dissolved in 500 centimetres cubed, it had a concentration of 0.1 grams per centimetres cubed. However, the most common units for concentration actually use a measure of volume called decimetres cubed. Now a decimetre is a tenth of a metre, or 10 centimetres. So a decimetre cubed is 10 cubed centimetres cubed, or in other words, 1,000 centimetres cubed. So in order to convert from centimetres cubed, or mil, to decimetres cubed, you need to be dividing by 1,000. So our 500 centimetres cubed becomes 0.5 decimetres cubed. And that means that our concentration therefore becomes 100 grams per decimetres cubed. So that's fairly straightforward maths you've hopefully met at GCSE. So here's an opportunity to pause the video and make sure that you are comfortable calculating concentrations in grams per decimetre cubed, given masses in grams and volumes in either centimetres cubed or decimetres cubed. So hopefully you managed to work out that 100 divided by 2 would be a concentration of 50 grams per decimetre cubed, 400 divided by 5 would be 80 grams per decimetre cubed, 250 divided by 5, because of course we have to convert it from centimetres cubed to decimetres cubed, will be 50 grams per decimetre cubed. 160 divided by 0.8 for the same reason will be 200 grams per decimetre cubed. 350 divided by 1.4 is 250 grams per decimetre cubed. 45 divided by 2.25 is 20 grams per decimetre cubed, and 18 divided by 0.9 is going to be 20 grams per decimetre cubed. Of course, in addition to being able to calculate concentration, you do need to be able to work out mass and volume from the other two quantities. So if we take our original formula and we want to get rid of volume on the right hand side, at the moment we're dividing by volume, so to get rid of it we multiply. So if we multiply, it disappears from the right hand side and it appears on the left hand side. So we can now say that the mass of the solute is going to be calculated by multiplying together concentration and volume. And then likewise, if we want to get rid of concentration from the left-hand side to leave volume on its own, at the moment concentration is multiplying, so to get rid of it we divide, and so it disappears from the left-hand side and reappears on the right-hand side. Now, when you're doing this, it's really, really important that you watch out for units, because what you're quite often going to find is that your concentration is given in grams or moles per decimetre cubed, but your volume is given in centimetres cubed. And if they're not the same unit, if they're not sort of the same size, then you're going to end up with an answer that is out by a factor of 1,000. So really, really watch out for that. So again, here's a quick opportunity for you to pause the video and make sure that you are okay calculating mass and calculating volume given the other two quantities. So as we said, to calculate mass, we need to do concentration multiplied by volume, making sure that the volume in the concentration units and the volume in the volume units are the same volume, so they're both decimetres cubed. So in this first example, we've got a volume of 2 and a concentration of 35, so we just multiply them together to make 70 grams. In the second one, we need to watch out for the fact that we've got 500 centimetres cubed, which of course is 0.5 decimetre cubed, so we're then going to have 0.5 times 24, which is 12. And then in the third example, we're going to have 0.2 multiplied by 420, which is 84 grams. Then for our second set of questions, we need to use the idea that volume will be the mass divided by the concentration. So in order to make a 70 gram per decimetre cubed solution from 14 grams of solute, we're going to do 14 divided by 70, and we're actually only going to need 0.2 decimetres cubed of solvent to dissolve it. And then for our second one, we've got 4.2 grams divided by 70 to give us 0.06 decimetres cubed. And then for our third example, again, we've got a sneaky thing with the units. So you should know that there are 1,000 milligrams in a gram. So 84 milligrams is actually 0.084 grams. And in order to dissolve that to make a 70 gram per decimetre cubed solution, we're only going to need 0.0012 decimetres cubed of solvent. So concentrations involving masses are great if you're doing something that doesn't actually involve any reacting chemistry. So say if you're a geneticist and you're making agarose gels for gel electrophoresis, you don't actually need to know how many molecules are involved, you just need to know how much agarose to put in to stop your gel from being really floppy. But if you're going to do a chemical reaction and you want to know how much chemical A is going to react with chemical B, it's no good knowing that your solution has 100 grams of chemical A in it, because that doesn't tell you how much of chemical B you're going to need. So if you're going to do some actual chemistry, like say some titration, then you need your concentrations to be in moles per decimeter cubed, not just grams. So we're going to use basically exactly the same formula. We've now got moles of solute divided by volume of solvent. So for instance, if we have 0.2 moles of hydrochloric acid dissolved in 500 centimetres cubed, again we have to do that little conversion to make that be 0.5 decimeters cubed, but we're going to end up with a final concentration of 0.4 moles per decimeter cubed. So we could add an additional step here and do some practice of X number of moles divided in Y volume of solvent, but to be honest, if you can manage the mass ones okay, you don't really need to practice that step. So we're just going to kind of level up here. So here we've given you some masses of some different chemicals, and we want to know what the concentration is, but in moles per decimeter cubed. So your first step for each one of these questions is to work out how many moles do you have. And for that, you're going to need the formula mass is Mr. Mole. So you're hopefully familiar with this formula, and you know that Mr is really MR, or rather relative formula mass. So for each one of these chemicals, we're going to need to add together the relative atomic masses of all the atoms in them to work out a relative formula mass. And then we're going to use this equation, but we're actually going to rearrange it. So we're going to get rid of the MR from the right-hand side. At the moment, it's multiplying, so to get rid of it, we divide it. And what we get left with instead is mole is mass divided by the relative formula mass. So the number of moles of the chemical we've got is found by doing the mass, say 73 grams, divided by the relative formula mass of that compound. So we're going to take each one of these questions in turn, and to start with, we're just going to work out how many moles of each one we've got. So 73 grams of hydrochloric acid, my relative formula mass for hydrochloric acid is going to be 1 for hydrogen plus 35.5 for chlorine. And of course, 73 divided by 36.5 is going to give us 2 moles. So just pause the video quickly and try the next 4, just working out how many moles of each chemical you have. So with a bit of luck, you've now worked out that we've got 0.1 moles of sodium chloride, 0.2 moles of nitric acid, 0.8 moles of sulfuric acid, and 0.7 moles of potassium fluoride. So now I know how many moles I have dissolving, I can do the same concentration calculation that I was doing before to work out what my concentration is. So for instance, for the first one, I have 2 moles in 2 decimeters cubed. So that's 1 mole per decimeter cubed as a concentration. So now pause the video again and see if you can work out the concentration of the last 4. So hopefully that's come out for you as 0.02 mole per decimeter cubed, 0.04 mole per decimeter cubed, 1 mole per decimeter cubed, and 0.5 mole per decimeter cubed. So the final stumbling block for concentration calculations, before we get to the actual titration bit, is questions that ask you to convert between a concentration in grams per decimeter cubed and a concentration in moles per decimeter cubed. And this seems to be a really scary thing for a lot of people. But here's the thing, you already know how to convert something that's in grams to something that's in moles. If I want to work out the number of moles of something, I know that I take the mass in grams and divide it by the relative formula mass. Well, concentration conversions are no different to that. You've got per decimeter cubed on both sides. So if you want to work out something in moles per decimeter cubed from something that's grams per decimeter cubed, it's exactly the same as working out the moles from the grams. The per decimeter cubed bit is on both sides, so you can just ignore it. All you're doing is dividing by the MR. So finally, we've got 5 calculations here, 5 concentrations expressed as grams per decimeter cubed, and you're going to convert them to moles per decimeter cubed, in each case just dividing by MR. So if we take this first one, 7.3 grams per decimeter cubed of hydrochloric acid. and we know that the relative formula mass of hydrochloric acid is 36.5. So 7.3 divided by 36.5 is a concentration of 0.2 moles per decimetre cubed. So pause the video, have a go at the last four, and then we'll check back together. So hopefully you worked out that my sodium chloride solution had a concentration of 0.2, my nitric acid had a concentration of 0.6, my sulfuric acid had a concentration of 0.08, and the potassium fluoride had a concentration of 0.75 moles per decimetre cubed. Hopefully you found that useful and you're ready and raring to go for some titration calculations. Don't forget to subscribe.